We're looking at quantum computing's threat to encryption, preparing for post-quantum cryptography.
And our mission really is to get a handle on this threat, understand what it means, and explore the steps being taken to prepare, for this post-quantum future. Welcome to the Cybersecurity Podcast series.
Glad to be here.
And just quickly, folks, you can get connected with Sudhakar Kakanada on LinkedIn for a quick chat on how he can help enhance your organization's cybersecurity to the next level of robustness.
A valuable resource indeed.
So today, we're diving into something, pretty fundamental for our digital future. The threat quantum computing poses to our current encryption.
Yes, it's a topic with significant long-term implications. We're looking at quantum computing's threat to encryption, preparing for post-quantum cryptography.
And our mission really is to get a handle on this threat, understand what it means, and explore the steps being taken to prepare, for this post-quantum future.
Absolutely. The fundamental concern boils down to speed. Quantum computers, at least theoretically, can perform specific types of calculations exponentially faster than the computers we use today.
Exponentially faster. And that speed is the key issue for encryption.
It is. Because that capability directly threatens the mathematical foundations of many widely used public key cryptography algorithms, the ones securing so much of our online world.
Okay, so we're talking about the security behind, everything. Online banking, shopping, secure communications. Things like RSA and ECC.
Exactly those. RSA relies on the difficulty of factoring huge numbers. ECC uses something called discrete logarithms on elliptic curves.
Right. Problems that are just too hard for our current classical computers to solve in any reasonable amount of time.
Precisely. They're computationally infeasible for classical machines. But here's the catch. Quantum algorithms, specifically Shor's algorithm, are, tailor-made to solve exactly these kinds of problems efficiently.
Shor's algorithm. Okay, so a powerful enough quantum computer could, theoretically, just break these current standards.
In theory, yes. A fault-tolerant quantum computer of sufficient size could crack RSA and ECC relatively quickly. Now, such machines don't exist yet.
Okay, so it's a future threat. But I've heard people talk about retroactive decryption. That sounds worrying even now.
It is. That's perhaps the more pressing near-term concern. Even if these quantum computers are, say, a decade away, data encrypted today using current methods could be harvested now and stored.
Stored until
a quantum computer capable of breaking the encryption becomes available. Then all that stored data could be decrypted retroactively.
Wow. So information we think is safe now might not be safe in the future from someone who's already collected it.
Exactly. Think about data with long-term sensitivity, government secrets, intellectual property, personal health records. The implications are significant.
So the cybersecurity world isn't just waiting for this to happen, right?
Yeah.
This is where post-quantum cryptography, or PQC, fits in.
Correct. PQC, sometimes called quantum-resistant cryptography, is all about developing new cryptographic algorithms. The key goal is that these new algorithms should be secure against attacks from both classical computers and quantum computers.
Building the new locks before the quantum keys are widely available, so to speak.
That's a good analogy, yes. We need these new quantum-resistant algorithms researched, standardized, and ready for deployment before the threat fully materializes.
And it's not just one new type of lock, is it? I understand there are several different approaches being explored.
That's right. It's not a one-size-fits-all solution. Research is active across several families of PQC algorithms. For instance, there's lattice-based cryptography.
Okay, lattices. Complex mathematical structures.
Yes, based on problems within those structures believed to be hard for quantum computers. Then there's code-based cryptography, which relates to error-correcting codes.
Interesting. What else?
We also have hash-based signatures, which rely on the security of cryptographic hash functions, something we already trust quite deeply. And there are others, too, like multivariate polynomial cryptography and isogeny-based cryptography.
So a diverse set of potential solutions, all based on different types of hard math problems.
Exactly. Diversification is good here, as it gives us options and resilience.
Okay, so for organizations listening, this sounds like something they need to start thinking about, even if the threat isn't immediate. What are the practical first steps? And folks, remember, you can get connected with Sudhakar Kakanada on LinkedIn for a chat about enhancing your organization's cybersecurity.
The absolute first step is assessment and inventory. Organizations really need to understand where they're currently using vulnerable public key crypto, like RSA and ECC.
Map it all out.
Yes, know your systems, know your applications. Then you need to understand the data being protected. How sensitive is it? How long does it need to remain secure?
Because that helps prioritize the migration effort later on.
Precisely. High sensitivity, long lifespan data needs attention first. And critically, organizations need to stay informed, keep up with the standardization efforts, especially from bodies like NIST, the U.S. National Institute of Standards and Technology. They're leading the process to select and standardize these PQC algorithms.
It sounds like preparing for a big infrastructure upgrade, almost like preparing for Y2K, but for cryptography. It needs planning and awareness.
It's a very apt comparison in terms of the scale and importance of the transition. Developing and deploying PQC is fundamentally a proactive step for long-term digital security. It requires foresight and a real commitment.
This is definitely a race against time, developing the defenses before the threat fully emerges. It's quite fascinating. It really makes you wonder, and this is a question for our listeners. How is your organization starting to approach this cryptographic transition? Are you thinking about it yet? And one more time, get connected with Sudhakar Kakinada on LinkedIn to discuss boosting your cybersecurity posture.
It's a critical question for anyone responsible for sensitive digital assets. The planning needs to begin sooner rather than later.
Absolutely. Well, that's all the time we have for this deep dive. Thank you for the insights.
My pleasure.
Stay safe and stay secure.